All right, zeros of a polynomial function. I've had lots of issues trying to record on my iPad and it still isn't working. So here we are using Zoom as my recording device because I'm desperate to get this recorded for you guys. All right, zeros of a polynomial function are the x-intercepts if it's real, meaning it could be, something as nice as 3. It could be irrational, which would be one of those crazy decimals that is typically something like 3 plus the square root of 5 or, something crazy like that. So we're going to talk about how do I solve that without the calculator. Obviously, I can find all of the real rational solutions by just looking at a graph and stating the x-intercepts. That does not help us with the irrational ones, and it does not help us if for some reason we did not have a calculator to know how to do it. So the rational zero theorem says that all the factors of the constant divided by all the factors of the coefficient are the only things that could possibly be a rational zero. Now, that's not to say that sorry, lost connection there. That's not to say that there would be irrational ones, but those are the only ones that it could possibly be. Okay. And so I'm going, give me just a second. It's going to make me stop sharing and reshare my screen here. Maybe. And so if I look at this, my constant is -3. So all the things, so factors of -3 are 1 and 3. And of course, they could be positive or negative, because if I had two negatives, it would, or if I had a positive and a negative, one of each, that's how I would get a -3. Okay. Then I'm going to divide that by all the factors of 4. So all the things that divide 4 are 1, 2, and 4. So which numbers did I use? I used -3 for the top and 4 for the bottom. And then I divide all of those numbers out, okay? So if I divide everything by 1, so 1 divided by 1 and 3 divided by 1, I would get 1 divided by 1 is 1, 3 divided by 1 is 3. Then if I went through and divided everything by 2, 1 divided by 2 is 1/2, 3 divided by 2 is 3/2, so that's 2 more. And then last but not least, divide everything by 4. So 1 divided by 4 and 3 divided by 4 gives me 1/4 and 3/4. So this would still kind of suck to have to figure out whether it would be a rational zero. So what that means is I would have to use synthetic division and see if I got a remainder of 0 for all 12 of these factors, because I have both the positive and the negative. So not super helpful when you have a long list like that. But in the two examples we're going to do today, we don't have near that many. So the constant divided by the leading coefficient in this case is -2. So only 1 and 2 divide 2. And the only thing that divides 1 is 1. So 1 divided by 1 is 1, and 2 divided by 1 is 2. So at most, I would have to do synthetic division 4 times to figure out the rational zeros, which, while not the best thing ever, it's still doable. So that's what we're going to do. -2 is first up. So if I use -2, my leading coefficients are 1, 1, -5, and -2. So I'm going to go back and do 1, 1, -5, and 2. Multiply the outsides, add straight down, repeat. And I do not get 0, so I move on and try the next one. So again, it's frustrating that it did not equal 0, but I didn't waste too much time doing this, so it's okay. Did not get 0 again. So my goal here is to get 0 as a remainder. Neither one of those did that. So I'm going to keep on going. I'm going to use 1. Try it again. All right, I got one more to try. Have I been forgetting a negative? I feel like I have. Yep. So if you caught this in the video, great job. This should have been a -2. So that would have changed these. Same here. This one should have been a -2. Luckily, it wasn't somewhere closer to the beginning because it would have changed a whole lot more than just that last number. But anyway, if that is a -2 and this is a +2, finally we get a remainder of 0. We only get that remainder of 0 if we actually use the correct coefficients. So make sure you do that. And if you caught that, good job. If you panicked a little bit because you couldn't figure out, didn't Miss Reidner do that wrong? You are correct. She did do it wrong. You got that. Good job. All right. So now that I have a remainder of 0, I have a function that is now x squared plus 3x plus 1. Anytime I have a quadratic, I'm going to use the quadratic formula. Yay, I know you're excited. So -b, b is 3, so it's -3, plus or minus b squared minus 4ac. So a was 1, c is 1, all over 2 times 1. I get -3 plus or minus 3 squared is 9, minus 4 times 1 times 1 is -4. So 9 minus 4 is 5. So my answers here are -3 plus square root of 5 over 2. -3 minus square root of 5 over 2. And then what was the original thing that gave me a remainder of 0? Because that is the other one. That is 2. Notice, I have 3 zeros. My original function was x cubed. X cubed is 3 solutions total. They may be imaginary, they may be rational, they may be irrational, but 3 total solutions. That's how I know that I have the right amount there. Okay, I did not need the 5th slide. All right, with irrational and imaginary, they always come in pairs due to the quadratic formula. Remember, you have the positive and the negative. So it will be 2 roots. There will never be 1 imaginary solution. There will always be 2 imaginary solutions, 4 imaginary solutions. There will never, no imaginary solutions because 0 is even. But there will never be odd number of solutions or imaginary solutions. Correction, there will never be an odd number of imaginary solutions. You can have an odd number altogether though. All right, let's look at one more example here. So if I start with factors of 13 divided by factors of 1, I only have 1 and 13 all over 1. So 1 divided by 1 is 1, 13 divided by 1 is 13. So it's always the top over the bottom. You cannot flip those and say that those are more. All right. So let's start with 1. I have 1, -6, 22, -30, and 13 as all of my numbers. I'm going to use 1. And on the first try, I got a remainder of 0. Thank goodness. So that's less we have to do. We can pause right there. So since 1 divides it evenly, I have x cubed minus 5x squared plus 17x minus 13. Right? Can't use quadratic formula yet because I'm not down to x squared. So I've got an extra step in between, which makes this problem longer. Kind of sucks, but you know, here we are. It's fine. Okay. Notice that I have 13 and 1 again. So I have the exact same rationals to try. I could try positive or -1 or positive or -13. So I'm just going to start where I started before. I'm going to start with 1. This time I'm going to use my new coefficients, 1, -5, 17, and -13. Okay. And once again, I get a remainder of 0. Thank you. I actually have the key, so I kind of cheated. But what that means is I have the solution 1. So don't forget it way up here. I have the solution of 1. Okay, so it actually counts twice. That's where that multiplicity comes in. So the sections you were doing before that were talking about multiplicity, here it is. This means that the factor x minus 1 happened twice. Okay, because it gave us a remainder of 0 and then a remainder of 0 with what was left. Okay, now what we have left is x squared minus 4x plus 13. We have a quadratic formula. So opposite b is 4, square root of -4 squared minus 4ac. All right, hopefully internet is back there. All over 2 times 1. If I keep that going, because I'm running out of room, so I'm going to go ahead and jump that down to the next slide. I get 4 plus or minus square root -36 all over 2. Square root of 36 is a perfect square, and it is 6, but since it is negative, I have to bring the I with it to state imaginary. All right, so my zeros are x equals 1, x equals 1, x equals 4. Well, this actually can go more to be 2 plus or minus 3i because it all divides nicely. So 2 plus 3i and 2 minus 3i. So 4 solutions. If I wanted to write out the factors, I would actually write x minus 1 squared, because there's 2 of them. And then I would not write out x minus 2 minus 3i and then x minus 2 plus 3i. That's not typically proper. So it's not proper to have the I in there. But I do know that the quadratic I was left with was x squared minus 4x plus 13. And I'm pretty sure I screwed up one of those signs. Hold on. Minus 4x plus 13. All right. So I have this as my factors. If something asks for factors, it's this. If something asks for zeros, it's this. How would I check if my factors are correct? Well, I would multiply them all back out. I would do x minus 1 times x minus 1, which would give me x squared minus 2x plus 1. Then I would multiply that by x squared minus 4x plus 13. Notice that's a whole lot of work, but my end result should be x to the fourth minus 6x cubed plus 22x squared minus 30x plus 13. All right, and again, I used one less slide, two less slides this time, actually. Okay, and then there's the fundamental theorem of algebra that says if f of x is a polynomial of degree n, so like if it's x to the cube or x cubed, so x to the third, then the equation f of x equals 0 has at least one complex root. And then there's also the factorization theorem, which says that we can turn any polynomial into a list of factors. If you do not understand that notation, that is okay. It took me many math classes and seeing it many times before I ever knew what the heck it was talking about. So that's okay. But just know that I can turn any polynomial into a big list of factors to solve. And that concludes 5B. So complete your homework now.